Good morning to you all. A warm welcome to everyone who is on stream with us right now. Let's make sure everything is technically sound. There should be a chat box to your right side. Please write something positive there so I know that you can hear me. I see a message from Roman. Can you please confirm that you can hear me? Oh, thank you, Dr. RK. So today here with me is Vladimir Krichevsky, who is a head of reservoir analysis department in Sofoil. Hello, Mr. Krichevsky. How are you doing today?
Hello, Artem. Thank you very much. I'm fine. Life is beautiful and amazing. Good to go.
Good. So the presentation today will concern blind test validation for pressure flow rate predictive models with an example of MRT. Now, before we begin, let me give you 3 short tips on the format of today's webinar. The entire stream will be recorded and saved on our channel, where you can rewatch it again. Throughout the webinar, please feel free to leave your questions in the chat box. And after the presentation is over, I will read out all these questions to Mr. Krichevsky, who will be happy to answer them. Bear in mind that we have around 15 minutes allocated to Q&A section. So in case your question was not answered, it will always be discussed later at NAFTA College Forum. So without further ado, let's begin. Mr. Krichevsky, a word to you.
Thank you very much, Artem. And thank you very much to all the attendees. Thank you for taking your time and joining our webinar. So today's topic is going to be blind test validation, again, for pressure flow rate predictive models with an example of MRT. Let me now turn off my camera and let's focus on the slides. All right. Again, this webinar is not on MRTs specifically, because I think throughout our series of webinars, we've been covering the topic of MRT a lot. So you must always look into our library of webinars. You can look it up on our YouTube channel, or you can see the list of the webinars on the NAFTA.college website. But still, the plan is to give you a very quick overview of what MRT is and what it does. And the main topic is how we tested the MRT predictive abilities with one of the major oil companies in Russia. So we're going to cover several synthetic tests. Then I'm going to run through the slides on the field tests. I'm going to show you the results, the conclusions, and then I'll be happy to answer all the questions. So let's go. First of all, what is MRT for? So MRT is a data processing technology which builds a predictive model of bottom hole pressures and flow rates. And the reason behind this technology, why we use this technology, is because, well, of course, when we develop any kind of reservoir, we are facing a lot of issues and challenges. So the most common issue is the production decline. When your oil production or gas production declines, that's not good news, always. And it could be caused by water cut increase or GOR increase. Also, the reservoir pressure around your wells can decline despite the fact that you have a balanced injection system. And sometimes you even inject more than you produce, but your pressure still drops. And that's always a bad sign and a bad news, and we need to know what's going on. So there could be many reasons behind this behavior of your reservoir and wells. So first of all, and most oftenly, we may experience cross flows, behind the casing flows or induced fractures which will strike our conformance. And unfortunately, we lose some injection into the water beddings near our oil or gas reservoirs, and thus we lose the reservoir pressure. Also, we may experience a premature water breakthrough or gas breakthrough if we have a gas cap, or we are injecting gas if we are on one of the cyclone projects, for example. The reservoir could be compartmentalized, and it could also severely affect the efficiency of the development and the water floods. And the productivity of our wells can also decrease in time. So in order to fight the issue, in order to address the challenge, we need to carefully distinguish between the reasons. And sometimes we don't have a lot of data. But if we have a database which contains the long enough recordings of flowing pressures, if we have any kind of pressure gauges downhole, and it could be a gauge on our ESP, or it could be a PDG, then we are happy to have a database of bottom hole pressure. And this pressure recording could be quite long. It could be several months or even several years. So given all this data, we may use the MRT technology to build a model which would describe the behavior of a reservoir and our wells, and give us a lot of insights, which in turn will provide us with the possibility to address the issues and make better decisions for more rational or economical reservoir development. So a quick overview of the technology. So in MRT, as I said before, we are using the pressure recording in our wells. So let's say in this horizontal well we have a PDG, and we have several years of bottom hole pressure history. Also, we have several wells surrounding this well in the center. And we put these several wells into a so-called MRT cell. So for this cell, we gather all the data which are available: the bottom hole pressures, the flowing rates, injection rates, and then we perform a mathematical procedure called multiple well deconvolution, which is a core of the MRT technology. So the goal of multiple well deconvolution is to automatically build a mathematical predictive model for several interfering wells. So it means that with the minimum human factor, we get this mathematical model which accurately describes the behavior of our wells, the way they impact each other. And given this information, we may get a lot of knowledge about the reservoir. So first of all, the first and the very quick result of multiple deconvolution is the decomposition of the offset well's pressure impact onto the well in the center. So now we may calculate what would be the bottom hole pressure in well number, well, in this case 11, if there were no wells around it. That would be point number one. And also, we may now calculate the impact of each surrounding well. So we may know, for example, if we have several injectors around it, we may know exactly how these injectors are supporting the reservoir pressure around well number 11, and which well is more and which well is less efficient in terms of pressure maintenance. The next step would be to reconstruct a reservoir pressure history. So once we have a mathematical model, we may always put a synthetic buildup at any time in history. And we may see what would be the reservoir pressure at any point in time if we had a pressure buildup at that time. So it means that no matter how many buildups you have in your history, and well, like in this case, we actually have none, but we may still reconstruct the history of reservoir pressure around well number 11. And we can see how it's been changing through the history, how it reacted to the offtakes and the injection into surrounding wells. And also now that we have the reservoir pressure history, we have the bottom hole pressure, and of course we have flow and rates, we may just forward calculate the productivity index. And we can also see how it's been changing through the history. And if we see some anomalies in productivity index, it could point us to some problems with the well itself. So the decrease in productivity index of a well can always show us something is wrong. Well, most often it would be a problem near the wellbore, so or in the wellbore itself. So if we have some sand in a well, or we have a lot of free gas liberating in the near wellbore zone, we may see it with the history of productivity index, and then we may decide what to do with different kinds of issues. So again, this is a very simple and a very quick overview of MRT. And now to the main idea of this slide. So whenever you face a new technology which claims to use your data and build any kind of model, and well, the purpose of any model is to, well, first of all, carefully describe the history, and of course, being able to predict. So these abilities could be tested. And there are several ways to test this ability. So you don't have to believe anything unless you actually see how it works. And there are several simple ways on how to test it. And I'm just gonna show you the story how we tested it with one of our clients in order to ensure them the technology is absolutely fine and we can work with the data with our service. So let's move on. So first, synthetic test number one. Let's call it a beginner level. So the model is pretty simple. So we have a homogeneous reservoir and we have several wells. So on this slide, I'm just showing you that first of all, we calculated the single well pressure response. So it means that in this model run, only well number one has been producing, while both wells 2 and 3 were idle. So we just now taken a peek on how well 1 is behaving when it produces alone. So later we need to test if we are able to reconstruct this behavior with the multiple well deconvolution and the MRT technology itself, right? And then to the actual test. In the actual test, we have several wells producing at the same time. So we can see that both flowing pressure and a buildup are distorted by the production of nearby wells number 2 and 3. And you see that the impact of these wells is quite severe, but still, and the picture on the right is showing it, we see that the single well pressure response, which was reconstructed with MRT, perfectly matches the single well pressure response, which has been pre-modeled numerically in this model, and we consider it absolutely true. So again, that was a very simple test. So we're showing the predictive ability. In this picture in the middle, I'm just showing you the quality of the match between the pressure that was given into the procedure and the pressure that has been calculated with the multiple well model, and you see that well, they match just perfectly, Right. So I say we pass this test. Again, this was a beginner level, very simple, and we pass it. Let's go further. I'd say the next test is more like an advanced level. And here we have a heterogeneous reservoir. So here in the left picture, you can see the permeability map, and you can see that the permeability has been quite different across the reservoir, and we have several wells here. And you can see that well 3 is sitting in around 20 millidarcy, and another well is sitting about 300 millidarcy. So you can see that the permeability varies well by different order of magnitude. So also in this test, the wells were either fractured or horizontal. So we advanced this test with the higher complexity of our completions. And let's move on to the test itself. So you can see the picture in the middle. It is a synthetic history of these several wells which have been producing simultaneously. You can see the different rates which are varying through the test for all the wells. And you can see the result on the right. So let me talk a bit about this result. So what we see in green dots, I don't know if you see the, well, there's a curve of green dots here. So green dots is a numerically simulated single well response for well number 1. And also you can see the black dashed line here, which is the result of a multiple well deconvolution. So you can see the perfect match again between green dots and a black dashed line, which actually tells us that we perfectly fit the single well pressure response for well number 1 in this case. And also on this plot, I put these blue dots, and the blue dots is actually the pressure buildup on this well. And I just put it on a log-log plot, so you would see that it is not very simple, in fact. So if we were just, to understand what are the properties around the well, and we would need to estimate the KH or skin of this well, and we only had the pressure buildup, it would give us the wrong impression about the reservoir and the well, because you see that due to cross-well interference, the shape of the build-up derivative is distorted. And, well, of course, it would affect the estimates that we would give with the standard PTA here. So that's the major difference between the standard PTA and using multiple well deconvolution in terms of studying the well and reservoir properties. You can see here that PTA could fail you if you have a strong cross-well interference, which is, well, quite often the case. And also in this test, we compared the cross-well pressure impact that we get from MRT to the one that we numerically simulated in the model, and we consider it like true. So you can see here that solid and dashed lines are numerically simulated, and MRT derived pressure impacts of well 2, 3, and 4 onto well 1. And I think you can, well, see here by your eye that, well, the quality of match is quite good. And, well, I think it's fair to say that this test is also passed. All right, let's move on to the next test. And, well, I think it would be quite fair to call it a nightmare level. So in this test, we had a two-dimensional model, and we had 12 wells. 3 of them were injectors, and 9 of them were producers. And they have been producing and injecting with different rates for, well, nearly 3 years. And you can see here that in all the history of these wells, there were no single build-up or fall-off. And now we need to build a predictive model using, well, we only had the rates and the pressures. Also, we knew the geometry of the reservoir and we knew where the wells were located, but the permeability field was unknown. We didn't know anything about the permeability distribution. So let me show you how we passed this test. So once we built the model and we started to test the predictivity of this model, we had like 3 stages of the test. So stage number 1 was to see how accurately we reconstructed the individual behavior of the wells. So what we did is let me show you here. So we have this 12 wells here, and we have, for example, well number 1, producer number 1. So here you can see how it's been producing. You can see the bottom hole pressure history when other wells were also producing or injecting. But what if this well were alone? Let's just erase all other wells and then use our MRT model to predict how the well P1 would produce if it were alone and it produced with a constant rate. So we just built a prediction. You can see that in this prediction, we first produced with this well and then we shut it in. So here you can see a classic behavior of the well in the closed system. And this is the MRT prediction. What we did next is we asked the oil company, who were the owner of the test, and they had a model in hands, to simulate the same scenario. So let's run the model once again, and only well P1 would produce, and then we would shut it in. And then we would just compare our prediction to what the actual model simulates, the numerical model. And you can see that once we plot these curves together, we see a very good match in a Cartesian plot. And of course, I would like to see how it looks on a log-log. And here on the right, you can see the quality of our prediction on a log-log plot. You can see the log-log plot for the production and a log-log plot for pressure buildup. So you see that, well, each plot contains 2 pairs of curves, the pressure and the derivative. And you see that, well, one of pair is green and the other one is purple. And, well, they match each other, well, close to perfectly, right? Okay, the next stage of the test is to predict what would be the pressure in a well if we shut it in right now. So once again, let's focus on well number 1, P1. So this well has been producing for, well, around 3 years. But what if we shut it now? What would be the buildup? Can this MRT technology predict a buildup without an actual buildup? And let us try to answer this question. So first of all, we use the MRT model and we predict a buildup. So you see, I added the buildup in the end. Well, it's actually, I think, about a month long. And you can see the pressure prediction for this buildup. This is MRT-based prediction. And once again, we ask our colleagues to simulate the same scenario in the numerical model. So that's exactly what they did. They just shot this well in a model, and they calculated what would be the pressure buildup. You can see that, again, the whole history and the buildup. Well, I can hardly see, but well, believe me, there are 2 curves here. One MRT prediction and one loaded from the numerical model, and they perfectly match each other. And now let's again check the quality on a log-log plot for a buildup. And yeah, so here you see that the build-up pressure and derivatives match each other perfectly for MRT-based and 3D model-based prediction. And now to the most thrilling part of the experiment. So we claim that we build a predictive model. And in this model, we had a lot of interfering wells, and we had pressure and flow and rates for all the wells. And actually, it gives us the ability to predict not only the pressure and the pressure impact of wells onto each other, but also we may actually predict the pressure and flow and rate for any kind of scenario. So it means that, well, for example, here we used the scenario like this. So we have this 3 years history of development. And now, at the end of the known history, we want to increase the injection. So all the injectors would raise the injectivity. And simultaneously, all the producing wells would be switched to constant BHP. Because before, they have been controlled by flow and rate. And now we want to freeze the bottom hole pressure. And the task is to predict how the flow and rate will change in all the producers. How would they react to freezing the bottom hole pressure and increasing the injection? And let me show you how it worked out for us. So first of all, we built this prediction with MRT. So for well number 1, again, you see that we, in around 3 months, we have stabilization of the rate, and you can see that we may actually look through the history, like, well, not history, it's actually the future. We can see through time how the flow and rate will change in the selected scenario. And then again, any scenario, of course, can be calculated in a numerical model. And let's see what was the calculation in a numerical model and if it matches our data. And well, yes. So we can see that the blue and orange curves, they show a very good match. And you see that MRT just proved the ability to predict not only pressures, but also the rates of the wells. So, which is quite important in many cases. All right, so now that you don't think that I only showed you the good wells with a good match, I'm going to show you the whole picture, right? So you can see that I'm plotting all the wells in this test, and you can see the quality of log-log plots match between MRT prediction and 3D model numerical calculation for both production and shut-ins. You can see the quality of the match. So each of the plot actually contains 2 pairs of curves again, right? And you can see that the match is very good. Sometimes we can't even see that there are 2 pairs of curves here. Now to the shut-ins. Okay, so we have all these wells, and you can see the quality of pressure build-up prediction or pressure follows, because some of these wells are injectors. You can also see that the quality of match is very nice. And then the quality of rate prediction. So again, for these scenarios, when all these wells switch to constant BHP and we simultaneously increase the injectivity, you can see that the quality of rate variation prediction is very good with MRT. So I'm again comparing the MRT prediction to what was numerically simulated on the initial model. So now we may see that the predictive abilities of MRT, which we claim, actually turn out to be true. And again, we didn't have the model itself at any time of this test. And only once we passed the results to our clients, and when we ran all these iterations of testing, all the stages, only then we saw what the real model was like. So again, we only knew the size of the model, and we knew the location of the wells, but we didn't know anything about the permeability distribution. And well, if some of you think now that, well, it's quite simple, what could be the permeability distribution? So, okay, we have like a small variation of permeability here, so it's not a big deal. We could reconstruct it using, you know, conventional workflow. And I'm just going to show you now how the real permeability in a model looked like. And again, we only knew it after we passed the test. And this is the permeability distribution. So you can see that the gray lines here are impermeable faults. This gray box is, well, close to impermeable, very low permeability, comparing to the average permeability in the test. And also we have high permeable channels. So between these two wells, and also we have a very weird channel from this well going through the fault and close to this well here. And also we have a local permeability increase around wells I1 and P2. So of course it's not geological, but I mean, when you need to test the predictive ability of the technology, well, it's not necessary to use well, realistic models. And our clients, they decided to use a model like this, and it was like a stress test. And this picture, I think it explains why I call this test nightmare level. Okay, so that is it about synthetic tests, but there's always another options of testing the technology. And we always have an option on testing it on the field data. So the idea of testing it on a field data is very simple. So our clients had several wells which had quite long pressure buildups. So they gave us the data on those wells, but before giving us the data, they deleted the buildups. So we only had the flowing pressures and these little pieces of buildups, which are, well, this is 100% wellbore storage. So our task was to reconstruct the deleted pressure buildups. And we only had a flow and pressure to train our MRT model. So let me show you the result for this particular well. Right, so on this picture on the left, you can see that the white dots is the restored, reconstructed bottom hole pressure, including the pressure buildups. And the green ones is the actual pressure buildup. So you can see here in the Cartesian plot, you can see the quality of match of the pressure. So we didn't have this pressure. And once we reconstructed it, it will nearly perfectly matched the actual buildups. And also, if you like to see buildups on a log-log plot, which I fully understand, you can see the picture on the right, which is the comparison between the log-log plot for an actual and the MRT predicted pressure buildup. And you can see that the quality of match is, again, very nice. So these are the pictures from our client. They are using Kappa software, and hence the pictures from Kappa, because I think from our history of webinars, I think you got used for us to use the pictures from our own software, which is called Polygon, and the pictures look, well, maybe it's not humble, but, well, I have to say, but our pictures look better. All right. So again, we had several wells like this. And after we passed this test, we built a statistical table on the errors and deviations between the predicted pressure buildups with MRT and the actual pressure buildups in history, which were deleted before they passed out the data. So you can see that the error is, well, quite low for all the properties which we need to estimate from the MRT. So you see that we have a very nice match on the bottom hole pressure. And if we were to estimate the KH or skin, also our relative and absolute error would be very low. So it, in fact, it means that if the data is good and we have a long enough history, then sometimes we may not even run the actual pressure buildup, but just use the MRT with this multiple well deconvolution inside to reconstruct the synthetic buildup and estimate the transmissivity and skin of your wells, and of course the current reservoir pressure around your well, without interfering into production, without a pressure buildup, without any production deferment. Okay, so I think this is mostly it. Let me show the conclusions. So, well, I think each one of you can conclude yourself based on what you just saw. So these are our conclusions. So the main point is whenever you deal with the any kind of technology which claims to build any kind of model, you may always test the abilities and the predictivity of this technology. And I just showed you through several slides, several cases, showed you the workflow of validation of the technology using synthetic and field data test. And well, I'm happy to say that with an example of MRT, in this case, the technology perfectly passed all the tests. And so I think it's safe to say that, well, at least for this client, for this data quality, the technology works just fine. And we may perfectly move on to performing any kind of jobs for this client with our MRT technology. Well, I think that's it. Thank you very much again. And if you have any questions on this technology or any, well, actually any questions, I'm happy to answer. Let's go into Q&A. Artyom?
Yes, thank you very much, Mr. Krichevsky. I personally very enjoyed this presentation. So yes, let's head to question and answer section. So the first question, actually there was a lot of questions and from Dr. RK, but from chat, I believe the question was resolved. Mr. Fabrice would like to know what is the algorithm behind MRT deconvolution?
Yeah, so again, shortly, let me describe the algorithm. So the algorithm behind the MRT is called multi-well deconvolution. So multi-well deconvolution is, again, a mathematical procedure which builds a mathematical model of several interfering wells. The core of this model are so-called unit rate responses. So if you're familiar with the deconvolution technology itself, it uses all the data available, all the data on rates and pressures, and builds a deconvolved unit rate pressure response for a well. So the difference of a multiple well deconvolution is that you have a whole matrix of these unit rate transient pressure responses. So you have the response of the well to the rate in this particular well, and also you have a unit rate response of pressure on the well to a unit rate production in an offset well. So in case you have several wells, well, let's say, for example, you have n wells, then if you have pressures and rates for all the wells, then you would have n square unit rate responses. And this would be the core of the solution of this multiple well deconvolution. So the procedure needs to find all these unit rate transient responses, and once we have this matrix filled, it means that we have the mathematical model of several interfering wells, which describes all the data which is available, with the maximum accuracy, and is also predictive. So again, in two words, this is how the technology works.
Thank you, Mr. Krichevsky. We have another question from Ms. Rushana Farahova. Can MRT estimate the current flow in contacts? And how does MRT predict the water cut of area or intervals with high water cut?
Yeah, very good question. So with MRT, we get the deconvolved response for a well. And it actually means that, well, let's say we erased all the wells around our well in the center, and we eliminate all the cross-well pressure interference. So now we are looking at the picture as our well would be alone in this region. So now let's assume that we have, well, for example, an oil-water contact somewhere outside our well. So now, having used the multiple well deconvolution, we have a very long, it could be several years long, unit rate transient response. And it means that if we see the mobility increase or a decrease when we face the oil-water contact, we may now see it on the unit transient response. And it means that before, if we use a classic PTA, for example, or RTA, we had a distortion caused by the cross-well interference. But now, as we erase this interference, we can see the real picture of reservoir. And it means that we may see the boundaries, the faults, or, for example, phase contacts like oil-water contact or oil-gas contact. That would be point number one. And the next part of the question was on water cut, right? I believe. So, yeah, in many cases, using just the results of the multiple well deconvolution, we may see, well, quite clearly which, well, for example, which injector is causing the water cut raise on our well. Because given the pressure impact history, we may always see and interpret this cross-well pressure interference with, well, sometimes even standard technology like PIT. And then we can see which well is the most suspicious for example, a water breakthrough. And we may distinguish between several wells, and we may, with a very high accuracy, we point to the source of the water breakthrough or water cut increase.
Yes, thank you very much. I don't see any more questions right now. So if you do have any questions, I think this is the last chance you pose them right now.
We've been talking about multiple well deconvolution and MRT technology a lot. So I believe we have a lot of attendees which have been attending our previous webinars. So I think many of questions on the MRT technology itself have been posed before. Yeah, so this is more like a story on the blind testing. So, well, actually, it's not about bragging, but it's about it's our vision of the right way to test the predictive technology. So, and here we have, well, very nice slides with an example of MRT, how it's been done with one of our clients. So that is actually the point of this webinar, I think the main point.
Okay, thank you very much. So if for some reason I missed your question, please excuse me, and we will surely discuss this question on our forum. The link will be provided in the chat. So if you enjoyed this webinar, then please put the thumbs up to this video and subscribe. We have a lot of other exciting webinars coming soon. So for all of that and more, we'll see you in the next webinar.
Thank you very much.
And goodbye.
Yes, and have a good day. Bye.